Hello, today I'm going to be solving 4.6 and 4.4/4.5 problems I created. Okay, so starting with 4.4 and 4.5. A square portion of the roof is missing and allows water to fall through to the floor, creating a perfectly square puddle that expands at a rate of 3 centimeters squared per minute. At what rate is the side length of the square puddle changing when the side length is 5? Okay, so what we know is we have a square puddle, and the rate at which the area is expanding is 3 centimeters per minute. So we know that's a rate for area. And then we are looking for the rate of the side length that is changing. So side length given is 5 centimeters. So I'm going to say side length is S equals 5 centimeters. And what we're going to do here is create a bit of a table to help organize everything. So let's draw this a line. Sorry about this. And because this is a square, we know that we can just multiply the sides or square the side. So area equals side length S squared. And then what we're going to do is define our variables. So we have area, and then we have side length. We know, given from the equation, that side length is equal to 5 centimeters. And because of that, we also know that 5 squared is 25 centimeters squared. And then we are also given a derivative of the area, or a rate of the area, and that can be written here. So derivative of the area is 3 centimeters squared per minute. And then we can find the derivative of this equation using the power rule. So that would be also dA over dt equals 2s ds over dt. And then we are looking for a rate of the side length that changes. So that would be this right here, derivative. And that's what we're looking for. So we can see that this variable is actually part of this equation, and this equation is the same as this one because they're both the derivative of the area. So we can go ahead and set those equal and solve. So 2s ds over dt equals 3 centimeters squared per minute. Then we can plug in our 5 centimeters for the side length. We'll get 2 times 5 centimeters ds over dt equals 3 centimeters squared per minute. We can go ahead and simplify this. 2 times 5 is 10. Divide by 10 centimeters on each side. And then what you'll be left with is ds over dt equals 3 over 10, sorry about that, centimeters per minute. Now, this unit right here came from canceling out this and this. And that's your answer. And that would be, let's see, answer choice A. Alright, now for question 4. Let W be a differentiable equation such that W of 6 equals 4 and W prime of 6 equals negative 2/3. The graph of W is concave down on the interval 4, 8. Which of the following is true about the approximation for W of 5.4 found using the line tangent to the graph of W at x equals 6? Okay, so already we know we are given an x value and a y value, and we are given, well, this is a derivative, so we can say this is our slope at a point 6, and the graph is concave down, which means, looking at these answer choices, it has to be, whatever approximation we get, it has to be an overestimate. So we can go ahead, knowing that, eliminate the answers that say underestimate. And then they give us an interval 4, 8, and we are looking for an approximation of 5.4 using the line tangent to the graph of w at x equals 6. Alright, so with this equation we can actually use point-slope form, which is y minus y1 equals mx minus x1. And here our y is basically our w. So if we want to, we can do w minus, and we're given a w value, which is 4. W minus 4 equals m, our slope, of negative 2/3. X minus, and our x value corresponding to the y is 6. And if we want to, we can go ahead and simplify this by adding to the other side. And now we're going to plug in our 5.4 and solve for w. So w of 5.4 is approximately, remember we're using an approximation, negative 2/3, plug in 5.4 for x, 5.4 minus 6 plus 4. And what we get when we simplify this is approximately 4.4. And that's our answer. And since we know that concave down means it's an overestimate, let's see, it is answer choice D. Thank you.